We're going to discuss linearization, and specifically, we're going to discuss first what it is and where it comes from in a Taylor series. Then we'll discuss a few applications as well as why we want to linearize. If we think of a graph, and I'll just draw it right here, we can have some function. I'll draw it in black. And we want to approximate that function. Let's say we want to approximate this function at this point right here. This is our x-axis. I'll call this point x bar. Now to approximate this, we'll take the value at that point, and then we'll also take the derivative at this point. There we go. That's good enough. And then we'll be able to use that derivative plus that point to approximate near x bar any new value of y. We'll make sure this is y, as any point along this line that we've created. Now this comes from a Taylor series. In a Taylor series, I'll just come down right here. We have some function f of x, which is approximated by f at x bar plus df dx evaluated at x bar, x minus, and then multiplied by x minus x bar, or the distance from that point. And that actually goes on for forever, where we have an infinite series. This is now squared, evaluated at x bar, x minus x bar squared, and this is all over, where can I write that? Right here. Sorry, just trying to figure out how to put that in there. We'll just add it right here. We actually have, this is actually times 1/2 plus dot dot dot. The function, or the series, is 1 over n factorial df dx to the n evaluated at x bar times x minus x bar to the n. And that's from n equals 0 to infinity. What we'll assume, though, is that these terms after the first derivative don't add much, and we just want a line. So we'll go ahead and we'll say those are equal to 0. And we'll just be left with this portion right here. So that comes from a Taylor series. And we can use this for a number of things. If we have functions that have logarithms or cosines or any number of transcendental equations in that ordinary differential equation, it makes it very hard to be able to accurately and efficiently do the math. And so we simplify it by making it a polynomial with this Taylor series and by linearizing it. We'll also use this in our Laplace transforms and our state space models. And linear models also make it easier to control, as we can assume that the output will be the same no matter where the change is. A change from 80% to 90% will be the same as a change from 10% to 20%. So let's go up here now and let's look at how we actually linearize and what the different elements are going on. Here we have dy dt is equal to some function, and we evaluate it similar to a Taylor series. We have right here, we approximate this function that's in terms of y and u as f of y bar and u bar, and that's similar to right here. We're evaluating it at the point first that we know. Then we'll take the derivative with respect to y, holding y bar and at the conditions of y bar and u bar. And the same thing right here, the derivative with respect to u with the conditions of y bar and u bar. Finally, we have these deviation variables we also sometimes call y prime and u prime. That's not because they're derivatives, it's because we're denoting that it's the difference between y and the y bar. Here, for example, if we were evaluating right here, and this were x, the difference right here we could denote as x prime. Let's go ahead now and let's look at an example of this. Change colors. Let's say that dx dt is equal to negative x squared. Let's write out our function one more time. Say that f of x is roughly f of x bar plus df dx evaluated at x bar x minus x bar. Let's evaluate this at x bar is equal to 2 to come up with our linearized equation. Our first thing will be to evaluate this function at x bar. So at let's say our function of 2 is equal to negative 2 squared, which is equal to negative 4. Next, we're going to want to take the derivative of f with respect to x at x bar, which is going to be negative 2 times x bar, which is going to be negative 4. Plugging this into our equation, we have negative 4 plus negative 4 times x minus 2. Distributing this 4 to both things inside that parentheses, we finally have f of x is equal to negative 4x plus 4. And there you have it. Let's discuss briefly one last simplification we can do to make this easier. I'll go ahead and just for time's sake, I'm just going to copy this right here and just paste it right here. Let's discuss now briefly. I'm just going to highlight everything that's going to be a constant. Our function where we specify the conditions is going to be a constant. Our derivative where we specify the conditions is going to be a constant. Our other derivative is the same case. And then we know these terms right here. So what we'll do actually is we'll give each of these a variable name so that we can look at these independent of each other. We'll call this alpha, this beta, and this gamma. And that's just so we can keep things separately. As I mentioned before, we'll call this quantity right here y prime, and this one u prime. These are what we call deviation variables. Or how far they are from that y bar term. I'll draw an arrow right there too. So our final equation can also look something like f of y and u is, make those squiggly, approximately alpha plus beta y prime plus gamma times u prime. Obviously this equation depends on which variables we have deviating and how many there are. If we had another one, let's say y, u, let's say t, we would have another Greek variable, let's say, I don't know. Let's say sigma times, if we said it was t, then it would be t prime. And sigma would be the derivative of f with respect to t. Just to give an idea of how that works. Let's go ahead and erase that. I don't want to confuse anyone, but just show that this equation isn't necessarily a plug and chug equation. It's an equation that we use to simplify. And then when we were to solve, we would just solve for alpha, we would solve for beta, we would solve for gamma, we would solve for y prime, we would solve for u prime, and then we would plug all of these in to get a linearized equation. Here, all this depends just on these two variables, y and u, and that allows us to simplify and plug stuff in. Let's go ahead and let's look at this example we have here now, and we'll go to MATLAB afterward to plug in the second two parts. We're going to evaluate this differential equation at the condition of u equals 16. And here's our differential equation right here. I'm going to go ahead and I'm just going to use this form right here to guide us. Here, instead of y and u, we're going to have x and u. So we're going to write x, 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 x. We have u. This right here we're going to write as our alpha term. Right here is going to be our beta. And right here is going to be our gamma. So let's go ahead and solve for those. alpha is going to be the function evaluated at x bar and u bar. We don't know what our x bar is, but we do know our u bar is 16. So it's going to be negative x bar squared plus radical 16 is 4. Next we have our beta. Our beta is going to be the derivative of this function right here with respect to x. So I'll go ahead and just copy it and say the derivative of this with respect to x. Obviously that radical u is just going to go to 0. And we're going to get negative 2x bar. Finally, we have gamma. The gamma is going to be similar. It's going to be d, that quantity, except with respect to u. And so we're going to have the derivative of radical u, which is 1 over 2 radical u on the bottom as well. And we know that u, or u bar I should say, is equal to 16. So we get a quantity of 1/8. If we plug this in then, we have our equation f of x and u is approximately negative x bar squared plus 4. I'm going to put this in a box, plus negative 2x bar times x minus x bar plus 1/8 u minus u bar. And that u bar is going to be 16. One final thing I want to discuss is the selection of our deviation variables, or these y bar and u bar values. If we select them such that y bar is equal to y at steady state and u bar is equal to u at steady state, then this term right here can go to 0. Let's discuss that just briefly. Our f is modeling the change in the system. And so if our values are selected such that f is a function of, let me back that up, wrong variable, y bar and u bar, that should equal 0 by definition, as these are steady state values, and steady state values do not have a change in system. So we can simplify our equation one step further, that alpha can go to 0 if we make sure that our x bar or y bar, whatever is within our deviation variables and wherever we're taking our measurements, is at steady state conditions. Alright, here we have our MATLAB worksheet for this lesson. We'll come ahead and we'll go down to the example. This is our solution for part A. Note that in this solution we already plugged in that f steady state and u steady state should equal 0. We'll move on to part B. Within part B, we're going to find a solution by setting dx dt equal to 0 and solving for x. That will allow us to find the steady state value of x. That's just what happens, is finding the value that makes the change equal to 0. We do that by taking our equation. We know that u is equal to 16, and so now we solve for s, which x, I should say, which should equal 2. Then we want to plug in our differences and simplify our differential equation. And mainly that just means plugging in our x steady state is equal to 2. And that simplifies to dx dt is equal to negative 4x minus 2 plus 1/8 u minus 16. There's some interesting things we can do with MATLAB to simplify this process and make it programmatic. Here in this code block, we declare x and u as symbolic variables, and we define our equation dx dt as equal to negative x squared plus the square root of u. Here we're able to use the diff function to output a differential, or the derivative on the right hand side. And as we print that, partial derivative of dx dt by x is equal to negative 2x. and the partial derivative of u is equal to 1/2 with a radical u on the bottom. Then if we plug in our steady state values of u equals 16 and x equal to 2, and we substitute those in with the subs function, we're able to find our answers of -4 and 1/8 for the partial derivatives. We can imagine this as a three-dimensional contour map, as you can see here, where we have a function space of both x and u and the corresponding outputs. Here to find 0, we need a correct combination of x and u. And with u set to 16, there's only one point along that line that intersects with 0 that works. An interesting thing on this contour map is you can easily see how we have this contour of the actual solution, and then our linearized model, which is that flat plane which intersects it. Finally, in part C, we want to simulate a step test both with small changes, so with plus or minus 1, and large changes with plus or minus 8. We'll be able to do that by changing this m value right here on line 69, which changes the magnitude of the step. We'll create our steady state conditions and create those conditions as an initial condition for our ODE 45. We'll also create the time points in the array n and make a linspace. We'll then create our input changes using changes within the array u. And we'll iterate through ODE 45 using x1 and x2 all, as well as t all. Our function returns two models, both the actual model, which is nonlinear, of -x squared plus radical u, and our linearized model with dx2 dt, which is -4 x minus 2 plus u minus 16 over 8. After creating a figure and saving our results, we can observe the differences between our linearized model and our nonlinear model.